Can you hear this, everyone? Who's watching on Twitch, can you hear it now? Okay, my sincere apologies about that. I will go over things again. I don't know what's going on. I have this microphone here, but even though it's plugged in, I don't seem to be getting any audio off of it, which is very, very odd. I don't know why. Maybe I have it in the wrong port. Give me just one more minute here. Can you guys hear this still? For those of you on Twitch? If you could let me know if you could hear this, this would be great. Okay, I'm actually seeing like audio processing on the computer, so I'm going to assume, okay, that you guys can hear this. I apologize. Apparently, Kubuntu does not like it when the Yeti is plugged into the USB 3 port for some reason. Whatever. Okay. So, yes, today is episode 17. This is CS350 Online. I apologize for the audio issues. There's actually a bit of a backstory to this and why your Piazza hasn't been answered yesterday. So as I was saying, while the audio was off, I was trying to install some packages and upgrade some things because there was some stuff I wanted to show you all today. And I was tired and I wasn't really paying attention to what apt-get was telling me to remove. And it had this big list of things. Hey, remove all this stuff. And I was like, oh yeah, I probably installed new versions of it. I don't know why it just didn't auto-purge the old versions. That's kind of weird, but okay. And you know, I didn't see things like SDDM being in the list as being a problem, which I should have immediately known. Hey, that's a problem. We don't want to uninstall that. And I just auto-removed it and I ended up pooching the Linux install completely. So yesterday, I spent the whole day reinstalling and getting everything to work again, which is why, of course, we have audio issues this morning because apparently when I installed the microphone, I put it on the wrong port. My apologies. Anyways, so today we're going to be talking about I/O and devices, which is how does the operating system actually communicate with things like your clock? How does the operating system communicate with your keyboard and receive input from the keyboard and things like that? So that should be lots of fun. And again, don't forget to read your quizzes or do your quizzes and assignments that are posted on Learn. First, of course, we need to look at the OS of the day. So let's go over there. There we go. So the OS of the day today is one that you might have heard of, and at the same time, I wouldn't be entirely surprised if you hadn't heard of it. It's called OS 2. It stands for Operating System 2, and it was released in 1987, and this is another joint collaboration between Microsoft and IBM. IBM is not doing very good with releasing their own operating systems and getting them out on time. No, that's just the early 80s, right? So Operating System 2 is designed for the release of their computer known as the PS2, which was massively, massively popular. Actually, you know what's really fun? We can just like find a picture of a PS2 computer because, you know, why not? So here's a picture of some IBM PS2 computers. And the ones that I remember in particular, you see these flat ones? These are the ones that I remember is these old IBM PS2s that laid flat. I never had any of the towers, although I'd certainly seen the towers, but I did have some of these flat ones. So when IBM came out with that machine, they wanted to come out with an operating system to go with it. And they wanted to give something more than DOS because, you know, when IBM arranged for the production of DOS with Microsoft, their own operating system that they were trying to develop, CP/M, was supposed to be a lot more functional and more capable than what DOS was. But when DOS got out there, the consumers didn't need anything else at the time, and so it just kind of took off. And even when CP/M did get released, it cost too much money, and no consumer would actually buy it. So when they released the new hardware, they wanted to have a new OS, but they realized that CP/M wasn't going to be the right OS for that, so they decided, hey, let's make a new one, and that was OS2, which was meant to serve as kind of an upgrade to DOS, and it was a pretty big upgrade, I can tell you that. This is an operating system I have used, by the way. So, I mean, it was DOS, but it had a protected mode. So if you remember from our last episode, I said that DOS didn't have this concept of separating the kernel from the user program. So there wasn't a lot of isolation going around. There wasn't any security. And it wasn't a big deal because it was the early 80s, and it was pretty rare for you to have a modem or to be connecting to things on the internet. Ironically, my IBM PC did actually have a modem, but I never actually used it. Because I didn't know how. I also didn't have a phone line in my room or an internet connection, so that would have been pointless. So they created DOS with a protected mode. They also added virtualization in, so virtual memory and things like that. And they also wanted to provide a desktop GUI, so you were actually like pointing and clicking on things. They wanted a better file system, so they created this file system called HPFS, which supported longer file names, larger files, and they made it interchangeable, so it was kind of compatible with that. And to be honest, the FAT file system is actually probably the world's most compatible file system with different devices. And when we talk about the file systems in a week or two, what you'll see is actually that there's a reason why FAT is so supported is just because it's so dang simple. Although it is very restrictive also. We'll talk about that another day. Another thing they wanted to support was multitasking and multiple CPUs. I mean, in the 80s, you weren't looking at a lot of computers that actually had multiple CPUs, but I remember late 80s, early 90s, Supermicro was releasing, and I mean, I'm sure other motherboard companies were doing it as well, but Supermicro actually had, and I remember this because a friend of mine had them, had a motherboard that had 2 CPU slots on it. So you could actually physically put 2 physical processor chips on the same motherboard, and that would work. So OS2 was an operating system that actually supported this, whereas DOS wouldn't know what to do with that. And they wanted to support multitasking. So a little bit of concurrency between it, which was pretty big for consumers. Now keep in mind, at the same time, you've got Unix and OpenVMS and Solaris, and they've been supporting fully preemptive time-sharing concurrency for decade at least prior to this. So this is not a new concept, but it's new to consumers because most consumers weren't using Unix-based or BSD-based operating systems at the time. The other big thing that OS2 wanted to be was compatible with DOS and Windows applications. And that's actually a really big thing at the time, because if you want somebody, like a consumer, it's not going to matter so much to them. But if you want a big company like a bank or like a law firm to switch to buying your hardware and say, okay, here's our new operating system, please use this instead, it gives you all these other features. That list of features doesn't usually mean much to them, because what they need to make sure is that whatever software they already have running, it will keep running. And you're not going to convince people to change operating systems unless you can promise them that whatever they have right now will continue running in the future in the exact same way that they expect it to. Because, and the reason they don't want to make that change is if they change it, then maybe they have to buy a new license. Maybe there are new bugs that show up in the code too when they do it, and they don't know how to fix it. So you've really got to make it backwards compatible, and that's what OS2 was. Now, this was Windows. Microsoft Windows did actually exist at the same time as OS2, and it was pretty big competition to Windows. OS2 was not popular amongst the consumer. It was more popular amongst businesses and schools. I know my high school actually had at least one. I want to say there were 2 OS2 labs. But the students didn't use them, and I'll talk about that in a minute. Another thing that you found OS2 running on you can actually still find OS2 running on them today, is called Pos Devices. Now, when I was a co-op student and somebody dropped a Pos device on my desk, I didn't actually know what Pos stood for. So I thought they were affectionately calling the pile of circuit boards they dumped on my desk piece of shit device. That's not what POS stands for. It's so not what it stands for. POS stands for point of sale. It's like a receipt printer from like a restaurant or a cash register from a grocery store. That's a point of sale device or a POS device. Yeah. So it was still funny that I thought it meant something else, but oh well. In the end, the reason why you don't know about OS2 or you've never used it is because it lost to Windows. And to be honest, I think one of the big reasons it lost to Windows was probably price, but usability. It was so my high school had a large number of computer labs, and you're probably thinking I grew up in Toronto. No, I definitely didn't. I grew up in the country, out in the middle of nowhere, and for some reason, we got lots of funds for computers or something. So we had tons of computer labs running all different kinds of operating systems and hardware, and the OS2 labs that we had just weren't touched by anybody. And I think it was because it was just a really difficult to use operating system. And so I have a picture of it, actually. So this is a picture of OS2 Warp, which actually would have been the version of OS2 that I tried to use when I was younger. And I mean, if you look at this today, this looks pretty straightforward. I think any of us could sit down quite comfortably and use this. We've got overlapping windows. Yes, we have some very old-fashioned tile-based textures. But keep in mind, what you're seeing here is a picture into the mid-90s. And that was like super popular. I mean, you've got icons, you've got, I know you can't see it here, but there's a little OS2 Warp menu. That would be like the start menu. But this was it was difficult to find things, and it was difficult to launch programs, I found. And if you compared this at the time, the lab in my school that was right beside the OS2 Warp lab was a Windows 3.1 lab. And I feel like we all got the hang of that pretty well. And people just preferred to use it because it was easier. The other thing was, I don't think anyone could figure out how to connect to the internet on OS2 Warp. And that was a pretty big thing because nobody where I'm from at that point in the early mid-90s had internet at home. So being able to use the internet at school was a really big deal. And so we just couldn't figure it out. So in the end, OS2 lost to Windows. And it happens. It happens. Not every OS wins. All right. So what I want to talk to you today about, though, is devices. And when we're talking about devices, we're talking about lots of different things. We're talking about different ways or different tools by which a computer is going to receive input and produce output. So for example, what was giving me trouble this morning, and I know my green screen filter is a little bit off here, but I've got this lovely microphone here. This is an input device. And the camera that you can't see because it's over there mounted to my wall, that's also an input device. And we've got all kinds of other input devices. Of course, you've got your mouse, and you've got things like a tablet, so writing tablets. You've got keyboards. There's many different kinds of peripherals that you can actually have for your computer that would be considered input devices. And we also have lots of different peripherals for our computer that we consider output devices. So things like your screen, a printer, maybe you have a second screen, your speakers, all of those devices are output devices. And then we have things that are input and output. So if you have a touch screen, so I've got a little Surface Pro over here, and it's input output because I can see on the screen, but I can also interact with the screen, so I can touch it, and that will actually send information into the operating system. But there's more devices than that. And this is actually kind of interesting. So one of the most important devices in your computer is actually the clock. And you might be thinking, is there like a physical clock device? There is actually a physical clock device on your motherboard of your computer. And the clock is very, very important for your computer. I mean, it tells you what time it is, but it's also responsible for part of the implementation of preemptive concurrency. And that is an actual device on your system. And then you have other kinds of devices too, like you have your disk drives. So, I mean, maybe you have SSDs, maybe you've got little M2 devices, whatever you've got some kind of persistent storage in your computer. Now, this computer that I have right here that I'm using has a little terabyte M2 SSD. It's a tiny little chip that stores a terabyte of data. It's great. Sorry, I can't show it to you because I can't actually move the camera because it's attached to like this rig over here. Also because it's hiding underneath one of the heat plates, so you can't actually see it. But any kind of disk drive, whether it's a mechanical drive or just a little M2 card, you have some kind of persistent storage, and those are all considered devices. They are pieces of hardware that your operating system is going to need to interact with, whether it's by input or receiving output from them. There's also things like the serial console, which is used for character input and output. Kind of, you can think of it as a terminal. You've got things like your network card. I had one around here somewhere, but I'm not sure. It was just a little 10 gig Ethernet card. And that in itself is a device that's used for input and output. There are so many different devices on your computer that we don't even think about because they're actually physically in the box, but they are there. And the question is, how do we actually talk to these different devices? So I want to show you something neat, really neat. So I'm going to minimize this. And hopefully you can read my terminal here. I suppose I could make it a little bit bigger. Well, just temporarily. Okay. So the directory I'm in right now on this computer is /dev. So this is a Ubuntu machine. This is running a Linux kernel. And when I go into the dev directory, you'll see a whole bunch of things. What are all these things? These are devices. These are devices and ports that your computer might have. And what's really interesting about this is that you can actually treat in Linux and in Unix-based operating systems, devices are actually treated like files. And that's really kind of neat because it makes interacting with those devices actually fairly straightforward. Now, for some of these, you actually need special drivers to make that work. So, for example, I don't see any USB devices in this list. But I do see an absolute ton of these TTY devices. And TTY is usually the serial port. Now, this machine I don't actually think has a serial port. I do not know why there are so many serial ports listed here. But if you had a printer attached to one of these serial ports, you could actually issue a command to your printer to get it to print something by sending some special assembly language to the serial port. So you would be literally doing something like if I were to do that, then that would actually cause, if I had a printer attached to TTY0, then it could actually cause that printer to print blah. It's pretty neat, right? So we can actually see a bunch of the different devices that we have, and we can interact with them a little bit through this. And I mean, there's other things in here too. So it's one that's in the devices folder is the null. So dev null. That's where you dump stuff that you don't care about. And then standard error, standard in, and standard out. That's like your serial console device. So we can actually do that. See, echo blah to standard out, echo blah to standard error. You could do things like that. It's pretty cool. And when I echo blah to null, you'll notice nothing prints because null captures whatever you dump to it and just tosses it. So this is pretty cool. Oh, sorry. I missed the USB because it was a folder up there. But this is a picture of the different devices that you can interact with through the Linux kernel. Now, this is not really how Windows does it, but this is how Unix-based operating systems do handle communication with devices, is as files, which is really cool. But there's more to it than that, unfortunately, because that's, even though the user can treat those devices almost as files, there's obviously going to be underlying support for how do I actually communicate with that device in the kernel. And how do we know exactly how we can interact with those devices? So before we talk about the devices themselves and how we would know how to interact with them and tell them what to do, a couple just terms that I want to review. And if you've, well, of course, you've taken CS350, but of course you probably forgot it. Just a couple important things. So one is a bus. That is, it's kind of like a wire. It's a communication road, and it'll have a bunch of devices connected to the bus. And what's interesting is when you put a message on the bus, you might be thinking, okay, well, this message needs to go from the clock device to my disk that's also on the same bus. And so you might be thinking to yourself, okay, the message goes onto the bus directly to the disk drive and dumps it there. And yes, the disk drive will get the message from the clock, but what's really interesting is how buses work is everything that is attached to the bus gets every message that goes down the bus. And so messages on the bus actually have to be addressed for who they are meant to go to, so that when each device sees messages going along the bus, they know which ones to ignore and which ones to keep for themselves. So we have these buses that are used as these big communication roads inside of your computer, and there's a few different ones, and they are actually connected to each other. So there's the internal bus, also known as the main bus, and that is what goes from your CPU to RAM. And it tends to be like the fastest bus on your computer because we want communication between the CPU and RAM to be super, super fast. And then there's the peripheral or expansion bus. Some people call it the PCIe bus these days. And that is another bus where devices are going to be able to send and receive messages from. And the two buses are connected with a bridge, which lets messages go from one to the other. Because obviously, we need devices to be able to send messages to the CPU, and devices are going to need to be able to interact with RAM in some way. So we need some kind of bridge to go between them. So just a couple things to remember. Sorry, I always get the scroll direction wrong because I flip it between using this machine and a Mac all day, and they have different scroll directions. I should probably switch the scroll direction so they're both the same. All right. So first off, a little bit about the devices themselves. So what's interesting is that devices have a little bit of computation power on their own. So it may not look like it has much computation power, but something like this little Wacom tablet actually needs to have some communication power or some processing power on board so that it can send data to the computer and the computer can receive signals back from the computer. And because it has a little bit of processing power, even your mouse and your keyboard has a little bit of processing power. With that, they need to have registers which are used to issue commands to the device, but also to send, to give responses back to who's ever on the other side. And we call these are registers that are actually physically on the devices themselves. And there are three primary kinds of these devices. There's status registers, command registers, and data registers. So a status register is typically a register that you're going to read on the device because it's telling you something about the device's current state. So for example, if we were looking at, say, this mouse here, one of the registers, status registers that this mouse here might have is something like, so this is a switching mouse. which means that this can actually connect to 3 different computers, and you push this magic button here and it will switch between attaching the mouse to each of the 3 different computers. So there's going to be a register somewhere on this mouse's hardware that indicates which switch, what the value of this switch is. Is this in mode 1, mode 2, or mode 3? Oops, if I don't do that. So status registers might also tell us what time it is. A status register might tell us whether our printer is out of ink. There's all different kinds of status registers that we might have. They usually are telling us something about the device's current state. Sometimes it's error codes, it's all different kinds of things. A command register is typically a register we write to, and it's us in the kernel telling the device we want you to do something. So if I were to write print to a device register on a printer, that might be a cue for the printer to actually start printing a document. I could write a command to a command register on my clock to make it beep, for example. Command registers are used for telling the device to do something. Write some data to a specific location on a disk, beep, turn a light on, all kinds of things like that. And then we have data registers. Now, data registers are a bit bigger than status and command registers typically because they are used to actually transfer data to and from the device. Now, something like a mouse has a little bit of data because it's going to have a position. And, something like this little tablet over here is also going to have positional information, but it's also going to have pressure information. And that could be, instead of having separate device registers for each of those, we could actually put it all into a data register. And your keyboard might have a transfer buffer, which is used to get data from the keyboard into your actual computer. So there's lots of different data registers. They're also used for things like writing a bigger chunk of data to disk, for example. Now, what's really interesting is because hardware space is limited and it's expensive and we don't want to use too much, a lot of the time we actually combine these registers together. So if we'll create a status and command register where if we read the register, it tells us the state, and if we write to it, we're telling the device what to do. So we often combine these, and you can even have command and data registers. So there's all different kinds of combinations. And again, these registers are actually on the devices themselves. And when you buy a device, let's say you were an operating system manufacturer and you wanted to actually include a bunch of support for different devices, you would get these spec sheets from the device manufacturers that would tell you about what device registers they have, how each of those device registers should be used, and where you can find them or where they are expected to be found. And we'll talk about the found part in a bit. So the spec sheet I actually have up here is actually for OS 161's clock device, and it has 6 device registers. The first 2 registers are status registers, and please ignore the first columns here. We will come back to what these columns are in a bit. So we've got 2 status registers that give the current time in seconds and nanoseconds. Now what's interesting here is you might be like, how does it keep track of the time? Is this like telling me, how many seconds since, the first day, or what is this? How do we keep track of the current time? Well, the truth is, how we keep track of the current time on most clocks and most devices is by counting how many seconds or nanoseconds have elapsed since the epoch. And the epoch was midnight on January 1st, 1970. That's considered time 0. Now, what's really interesting about this, and I am going to briefly mention this column over here, is that you'll see that the size of this register is 4 bytes. So it's very conceivable that at some point we are going to actually run out of space in our time registers, and that's actually a known thing, and it even has a name. It's called the End of Unix Time. And it will happen in your lifetime, and it will happen in my lifetime too. It's not that far off. It's about 18 years off, actually 17 years now. So everybody here will still be around when this happens. And in fact, the date of the end of Unix time is January 19th, 2038 at 3:14:07 GMT. At that point, we will overflow the current time register on many hardware devices. And you might be like, oh my goodness, what's going to happen then? I'm not sure, because I don't know if we've really started even thinking about addressing the fact that the end of Unix time is coming. I mean, when it came to Y2k, we didn't address that until pretty close to when that happened. For those of you who are not familiar with the Y2k bug, what actually happened was in older computers, they didn't think about how many digits you should use to keep track of the current year. So they were only using 2 digits. So like the 1981 IBM PC, the first PC from IBM, it only used 2 digits for the year. And the question is, if you put 00 in, does the machine interpret that as 2000 or does the machine interpret that as 1900? And you can imagine a lot of systems were built thinking that it's going to behave a certain way, and it may not behave that way at all. So people had to rush to figure that out. And, you know, there was panic buying. People were filling up bunkers thinking that planes were going to fall out of the sky, and all these bad things were happening, could happen. I don't think anything happened at all, because I think it just didn't end up being such a big deal. And I'm sure the same thing will be true for the end of Unix time. There's different ways we can handle the end of Unix time. One of the ways that we can handle it is to create a new epoch. Another way you can handle it is to use more bytes for the current time, but we don't need to worry about it because it's still like 17 years off, and I have no idea what hardware is going to look like 17 years from now, because I don't even know what computers are going to look 5 years from now. Like, if you had told me years ago that I would have a 16-core desktop, I'd be like, no. Who needs that much power? Okay, yeah, I need that much power, but anyways. So that's the 2 registers that tell us the current time. Then we have some registers that are actually really useful for implementing preemptive concurrency. We have, the first one I want to talk about is actually countdown time. So the second from the bottom. It is a status and command register. And when you write a time to this register, it actually starts a countdown timer. It's pretty cool, right? And when you read it, it can tell you how much time you're counting down for. And let's say that, okay, you've initiated a countdown. What happens when the countdown expires? So it reaches 0. So when the countdown expires and it reaches 0, then this interrupt register will have a mark in it that indicates my countdown has expired. Please, and it will also fire an interrupt. And the idea, so this is actually how we're going to implement preemptive concurrency. We write the scheduling quantum to the countdown time register, and then when the countdown time expires, so when the countdown is stopped, there will be a value in this register here to indicate the countdown is stopped, plus the device itself will send an electrical signal to the CPU to say that something has happened. And then to let the clock know that we have handled this and please move on, we can actually write or clear the interrupt register to let it know, okay, we're aware. A lot of times, so this is an ACK. It's an acknowledgement. We are acknowledging to the device that we recognize it has done something and we have handled it. Now, this would be a bit of a pain in the butt, right? If every time the scheduling quantum expires, we have to clear this bit and then we have to restart the quantum all over again. Well, that's what this other command register is for. So restart on expiry, if we write to this register, then whatever our countdown is, once it expires, it will restart automatically, which is what we want, right? Because we don't want that extra delay having to handle the interrupt, clear the interrupt, and then manually restart it. So what this lets us do is it's going to let us restart our countdown, and then we will still clear the interrupt from the previous countdown, but we don't have to go through the business of manually restarting it each time. So that's kind of neat. And then the last command register on our clock device is a really cool one that you can't use in OS 161. It's the speaker. And most people, I think, today don't realize that your clock device can actually make noise. And I think that's because most of you probably haven't built like an old 486. You probably haven't built an old tower before. If you've built your own desktop, that's great, but it's not really evident that this exists. But back in the 80s and 90s, when you actually built your own computer, the clock actually had a speaker, a little crappy speaker that was attached to the front of your computer case to the motherboard. And that was it's a part of the clock, and you could do things like when the clock timer expires, you could tell the clock to send a beep, and it would beep out its speaker. So we have a command register on the clock to cause beeps. Now, this is actually used in really interesting ways. You actually still have this device on your computer. It's not like a physical speaker you see anymore. They've implemented it in different ways. But it used to be that how this is used, and I mean, Apple still does something like this, and various motherboard manufacturers actually still do similar things, but they don't all use auditory sounds to do it anymore. Apple does, though. What this is primarily used for is when you're booting up your system, there might be a problem with the actual hardware. So when your BIOS, which is the basic input-output system, it's what's used for making sure that your devices are there and everything's mapped appropriately and so on and so forth, and loading the first program, so your BIOS handles a lot of these hardware issues. If there's any faults, the motherboard used to send a signal to the clock through its speaker to tell it to play a particular sequence of beeps. So it might be like 3 long beeps followed by 2 short beeps. And if you looked it up in your motherboard guide, it would tell you, oh, that means that the BIOS battery is dead. So all of these different beep codes were actually diagnostics for what's wrong with the hardware. And Apple machines actually still use an auditory system for doing this. I want to say that PC-based hardware moved to flashing LED lights on the back of the motherboard. And now, so I have 2 Asus ROG motherboards, one in this one and one in my other computer, and they actually have a little LED panel inside that actually prints a code, so the actual numeric code. So I don't have to watch for blinking LED lights, and I don't have to listen for a beep code anymore. I can just look at those motherboards and they'll just tell me. And the reason why I haven't been using these desktops for very long is because my primary one, my Threadripper, actually had an error code 68, which was a problem with the PCI bus. Maybe, I don't know, because sometimes the error codes don't really mean much to a human who doesn't work at Asus. All right. Anyways, that's what the speaker is there for. It's there for, creating alarms, but it's also been really effectively used for diagnosing problems with the hardware. Okay. So here's another device called the serial console. And the serial console is used, it's kind of like standard in, standard out. It's used for getting characters from a keyboard and sending characters out. So getting character input and character output. And we have a serial console device in OS 161. And it only has 3 registers. The first register is a command and data buffer. And that is used for either storing the data read from the serial console, or it's where we write the data to output to the serial console. So that is if we write to it. So if we write to the character buffer, that's issuing a command to the serial console to tell it, hey, please write this character out to the standard out. And if we are reading from it, then we are getting data from standard in. That's kind of how it works. And then we have two status registers called write IRQ and read IRQ. And remember, IRQ means interrupt, and I don't know why that is the short form for interrupt, but it is, and it always has been. Now, what's really interesting about this device is that you can only do one operation at a time. So you can only be reading or writing the serial console at any time. And that's actually why we have these status registers here, because we need to make sure before we try to interact with the serial console that there's not currently an operation in progress. Because if there is an operation in progress, we don't want to start another one until it has completed. And the idea is once a write has completed, this status register will indicate it's completed and if there's an error. And if a read has completed, this status register here will indicate that the read is completed and any error codes. And of course, whenever they complete, the serial console will also throw an interrupt so we know to actually look at them. Now, what's interesting, though, is what happens if you were to try to have two of these operations happening simultaneously. So let's say you tried to use this device in such a way that you ended up trying to read from the serial console while you were writing to the serial console. What happens? Well, the device manufacturer says the following: behavior undefined. And that's really, really common in like device manuals and stuff. You'll see a lot of behavior undefined. And what that means is that anything could happen. The manufacturer has not specified what the behavior of the device will be if you attempt to do this, which means literally anything could happen. And you should be careful. So it means that maybe you get half of one character printed, or maybe everything gets corrupted, or maybe it magically works out. The point is it's undefined. The manufacturer says just we're not defining what the behavior is going to be expected. So be watchful for things like that. Now, obviously, that means when we are using something like a serial console, we're going to need to use some mutual exclusion on it. Which brings us kind of into our next topic of device drivers. So we've got all of these lovely device registers on the actual physical device. And now the question becomes, how do we actually communicate with the device to tell it, hey, write to the serial console, read from the serial console? How do we actually tell the device to do these things inside the kernel of the operating system? And that's what we have known as a device driver. And there are many different kinds of device drivers. The majority of device drivers are part of the kernel. And sorry, I'm just Googling a command here. So what I want to do is I want to show you, because I'm on a Linux machine, not a Windows machine. Most device drivers are actually part of your kernel, which means they run with kernel privilege, which makes sense because they're going to be interacting with your hardware. So what I want to show you now, I was just looking up the command because I couldn't quite remember it, is in Linux, we can actually show you all of the different kernel modules that are actually available. And these are device drivers. They are tools that we typically use to interact with devices. So I'm going to use a command called modprobe. And modprobe is actually useful for, you can list the modules that are on your system. You can turn one off. You can restart them. There's all kinds of things. So I know when I did driver development and I did driver development for Linux, we would use modprobe a lot because we'd want to restart our driver every time. So modprobe -L. And of course it doesn't want to work. Never mind. I'm using the wrong one. LS mod is the new one. It must be. So there we go. LS mod. Oh, look at all these things. Look at all these different devices. So let's see what kinds of devices we have. I have RF COM. That's a radio frequency communications driver. That's actually being used for my keyboard and mouse because these are Logitech switching mouse, and I use the unifying receiver for them, which is a little RF module. RF, by the way, means radio frequency. What else do we have here that's interesting? Some sound drivers. And we've got some video drivers here. We've got some things for the bus. That's the sound bus. You can see here we've got all different kinds of modules. These are all device drivers that have become a part of the kernel. So there's video, the Nouveau drivers for NVIDIA, of course. And, you know, we've got different PCI controllers, different bus controllers. I'm going to guess and say that's one of my network controllers. There's lots of different interesting things in here. NVMe, that's going to be for my SSD. Lots of fun things, right? So most of the time, device drivers are part of the kernel. And they're part of the kernel because they're going to be interacting with physical hardware. But that does not mean that all drivers are part of your kernel. In fact, they're not, especially on a Linux-based system. So, for example, printer drivers are often not, at least on a Linux kernel, are often not actually part of the kernel. So I actually used to work on Linux printer drivers, and they were actually living completely in user space. And the reason is what a printer driver does is it takes your document like this page here, and it's going to convert it, it's going to compile it into the assembly language of the printer. So that's pretty cool, right? And then once it's, you don't need kernel privilege to compile something into an assembly language. The assembly language isn't exactly secret for many printers. And then what happens is at the very end, at least all the printers I was working with, for the most part, not all of them, but a large number of them, were connected to the serial port or the parallel port. And all you had to do was write to dev.tty0, a file that represented the port, the physical port, and that would print. That would cause the printer to print. Now, obviously, the serial port had a driver inside of the kernel, but the printer itself didn't need a specific kernel module to do it. Now, that's not saying that that's true for every printer. That was for dot matrix printers and some older POS devices, but wireless POS devices like little handheld receipt printers and ones that connected over USB, they actually did require kernel modules because they would need to tell the kernel how to communicate over the wireless or how to communicate over USB to that particular device. So most drivers are a part of the kernel. They are a loadable part of the kernel, which means you can unload them and reload them. And that's true in most operating systems, even Windows, believe it or not. The way Windows used to do it, and I don't know if they do it this way anymore, because again, I don't really use Windows. I haven't in a long time. I mean, I have this Surface 3 here, but I don't really touch it much. It's got the Twitch chat open. How Windows used to work is there was a Win32 folder in your C drive, and that was actually where all the kernel modules went. So all of the loadable drivers that were all DLLs, they went in that directory. So if you were in that directory, it meant you were a loadable kernel module. That's kind of cool. All right. So that's kind of where they live. Device drivers, for the most part, are loadable parts of the kernel. They don't necessarily have to be, but most of them are. But what is inside of a device driver? So a device driver is going to tell us how to actually do the operation with the device. So for example, this sample device driver here is to write a character to the serial console. So remember how I said we're going to need mutual exclusion on the device? We're going to use a semaphore, a binary semaphore for mutual exclusion here. And you tend to see semaphores, binary semaphores, used with device drivers instead of locks. And it may not become completely evident today why we do that. But what I would like to say is this is what happens. When a device fires the thread that initiates contact with the device sometimes has to block and wait for the device to complete before it can continue back with whatever it was doing. So for example, if you wanted to write to disk, you need to make sure that the thread that wanted to write to disk blocks and waits for the write to complete before it continues on its merry way. So if we use a lock for that, then the thread that answers the call for the device is done doing the disk write is not going to be the thread that initiated the communications with the device, which means that the thread that recognizes the device is done working can't release the lock on the device. And we would have to switch control back to the original thread and have it wake up and then release control. That can be a little slow. Now, it's not really a big deal who always releases control of the device, in which case a binary semaphore is actually a perfect solution to the problem because a binary semaphore can be released by anybody. So you'll actually see binary semaphores used a lot in device drivers. It's not to say you can't solve this with locks. You absolutely can. It's just to say that it may not be the most efficient way of doing it. So we use binary semaphores instead. So what we do here is because we know we can only have one read or write happening at any time, we're going to P our binary semaphore for the output device. And then to tell the serial console to actually write the characters, we are going to write a character to the device data register. So going back here, we're going to write to our character buffer. And then what we're going to do is something called polling. And what polling is we're going to repeatedly then read from the write IRQ register until its status says it's done. When the status says it's done, we'll acknowledge completion by clearing the status register. And then we'll release our hold on the device. Now, this is one way that you can implement a device driver, and this is called polling, where the kernel driver is going to repeatedly check the status of the device until the device finishes. This is kind of a waste of CPU cycles because you could be doing something else. And the truth is, there's an easier way to do this. We know that when the device has done something, it fires an interrupt, which means it sends an electrical signal to the CPU. So an alternate approach to doing this is to split the device driver into two parts. You've got the write handler and then the interrupt handler for the device. So the driver part is going to get mutual exclusion on the device and then write the characters to the character buffer to tell the device to print them onto the screen. And then when the device is done, it fires an interrupt, and then we acknowledge completion back to the device and really release our hold. The advantage of this implementation here is there's no polling, so we are making better use of our CPU's resources. Now, you might be thinking to yourself, this is how every device works then, right? It uses interrupts instead of polling, and the answer is no. Actually, they don't. So what's interesting is that while the majority of devices do that, they don't all. So, for example, USB polls. And I was reading some specifications about USB, about why does USB poll as opposed to using interrupts. My understanding was and I skimmed the article lightly because I'm obviously not a hardware engineer. It seems to me that so for the existing lines, so the data lines that they already have for USB, if they wanted to send an interrupt over those data lines, it has the potential to corrupt data traveling over those lines. So that wasn't an option for them. The other option they had was to add an additional line, which they didn't feel they had the space for. So USB is actually polled. Now, what's interesting about this is your computer has a USB controller on board. And, I haven't read a lot of specs about those, but if I had to take a guess, the USB controller might actually do the polling itself and then might turn that into interrupts for the CPU, if I had to take a guess. Don't quote me on that, it's a guess. The point I'm trying to make is some devices are going to use polling and some are going to use the interrupt system. And that's actually a theme with devices. Because while we've shown you how to do the device driver and actually make a device do something and handle the response, the thing we haven't told you how to do is actually how do you talk to those registers? Like, do you just, is it like some inline magical assembly that you do where it's like, oh, I went to write to register USB. How do you talk to device registers? Because obviously everybody's system is completely different. The hardware that I have attached to mine is completely different from the hardware you have attached to yours. For example, in my machine right now, I have one of these little M2 drives. I have an RTX 2080. I have, a Wacom attached. I've got this Yeti. I've got the 4K camera. These are all attached to this system. But you don't have those same devices. So how can we label these registers? Well, we don't really do that. So there's lots of different options we have with actually communicating with these device registers, and I want to talk about some of them. So the first one is called port mapped I/O. And what this essentially does is we're creating a separate, smaller address space that's usually on the chip, and it is going to use fewer bits for addressing than regular RAM. And we're not going to call things addresses, we're going to call things port numbers. And we bind device registers to ports in this special address space. And then using special assembly instructions on x86 that's in and out, we can send data to these port numbers and receive data from them. So we can read and write these ports. And what happens is the devices are listening for these instructions, and they know what port numbers correspond to each of their device registers. So when they see an in instruction and port 45, and they're like, oh, port 45 is mine, and you want to write to port 45, okay, I'm going to take that data for myself from that port. So the devices are going to listen to the instructions going to the special address space so that they can grab and use the data and send it back as needed. Now, the advantage of this particular strategy is that it's actually very, very fast, because all of the communication going over this port mapped I/O, all of the devices, even though there's going to be lots of devices connected to it, the number of reads and writes from these different ports is much less than the alternate approach for memory mapped I/O, which means that the devices are going to be having to decode fewer instructions to figure out whether you're trying to talk to them or not. Disadvantages of port mapped I/O are the fact that it's very restrictive. You have to use these special I/O instructions. You can't use just general assembly instructions, so you can't do arithmetic in place in a port. You have to copy it out of the port, do it in regular memory, and then copy it back to the port. So your access to the ports is very restricted. The other downside is that because the number of ports is very small, very few simple devices can actually use this at any time. Now, an alternate approach is called memory mapped I/O, and what we're going to do is, instead of using a special address space for the mappings, we're actually going to use RAM. So we set aside a region of RAM, KSEG1, and part of KSEG1, or part of, that there's going to be a specific part of physical memory that is set aside to map device registers to. So we're just going to use regular RAM. So the advantage here is that we don't need special instructions because we're just reading and writing from RAM. The other advantage is that it supports more devices and more sophisticated devices than port mapped I/O. The downside is that all of these devices now have to be connected to the main bus, listening for addresses that are mapped to their device registers, which means they have to decode every signal that comes across the main bus to figure out whether it's for them or not. And that is slow because the number of instructions that are coming over that bus that are for them versus are not for them is mostly not for them. So they're doing a lot of address decoding for not a lot of benefit for them. So it's a bit slower to use memory mapped I/O, but it's more flexible. Now, what do we use today? Both. Some devices on your computer will use port mapped I/O, and some devices on your computer are going to use memory mapped I/O. We don't live in a world where we use one or the other. We use both, actually. And actually, there's more than this. OS 161, by the way, uses memory mapped I/O because it's a toy, and we don't care. All right. Really got to get these scroll directions figured out. So this is OS 161, by the way. And if you'll remember, we talked about KSEG1 was partially in use for talking to devices. And it's because now, because I'm using, and we use this tiny bit of memory of KSEG1, you're going to want to add A to this, A000000, and that will tell you what part of the region we're actually using in virtual memory, but it maps to the very last few bytes of the 512 megabytes that KSEG1 would map to. And KSEG1 or KSEG0 knows that that's where the devices are and won't use it itself. And so the idea is when we see a virtual address corresponding to a device, the nice thing is the kernel knows, oh, you're trying to talk to a device. So that's why we separate them. So for OS 161, what ends up happening is, so we have at the very end of the first 512 megabytes of physical memory, we have 32 slots, each slot being 64 kilobytes to be used for a device. So like the clock will have one of these slots, and the serial console will have a slot, and the disk drive will have a slot. Now you might be like, well, how do I know within the slot where each of the device registers actually are? Well, you do know, because if we go back to these spec sheets, it actually tells you. It tells you the size of each of those device registers in bytes, and the offset is where in the slot that device register is. So these spec sheets are actually really useful for telling us where in the slot these device registers will be mapped to. All right, let's go back. Now, what if I want to transfer larger pieces of data? So let's say I want to transfer like 512 bytes. I could use port mapped I/O, I could use memory mapped I/O, but that's a big chunk of data. How do I actually, does the device do that data transfer? What's going on here? So if we want to do larger transfers to the device, there are two special technologies we can use for larger transfers. One is called program controlled I/O. And what program controlled I/O is the device driver itself, so we're going to use the CPU, is actually going to be responsible for transferring the data from memory to the device's buffer. So the CPU will be involved in this task. The advantage to this is fairly simple. The disadvantage to this is that it means the CPU is busy doing this large data transfer when maybe it shouldn't be. Maybe we could use the CPU a bit better. So another option is called direct memory access, or DMA. And this is what most modern systems do for larger transfers. It's not to say program controlled I/O doesn't exist on your system. It's just to say, we don't use it that often anymore. What we use today is DMA, and the idea is that direct memory access is the CPU is going to initiate contact with the device and tell the device, hey device, I need you to do something for me. Here's what you need to do. You need to copy X bytes of data from this address. And then the disk itself is going to contact memory, and it's going to actually perform the copy itself. And then the disk will let the CPU know when it's done. Direct memory access. We're letting the device do the copying instead of the CPU, which means the CPU is free to do other things. Now, this is a really simplistic picture of DMA. In truth, there's actually something called a Dma Controller, which is a separate device, and it gets involved with handling how to set up the transfer of data between memory and the device. So there should be some extra pieces in here, but we're going to keep it simple because it's just a high-level understanding. OS 161 does not have a DMA controller, so it just uses program controlled I/O. Again, it's not really a big deal because it's a toy operating system. All right. So that's actually where I'm going to leave things for today. In our next episode, which will be Tuesday of next week, of course, we are going to start talking about a specific kind of device that's really important to you, and that is this concept of persistent storage. So we'll look at kind of the history of persistent storage, and then we're also going to look at hard disks, so how do mechanical drives work, and we'll probably, I think, even get to hopefully talking about SSDs and how SSDs work, and we'll talk about how to write the drivers for these particular tools and so on. So hopefully that will be interesting for you, and we will see you then next week.